the audio bouncing? Is there like a bar? It's all right. Very good. Very good. Heavenly Father, we thank you for today. I thank you again, Lord, for these students. Pray to be with us. Help us to glorify you in this time, Lord. In your name I pray. Amen. All right. So I want to talk to you about the concept of flux. And people have this tendency of throwing around certain slogans about flux in physics, and these slogans require, I think, some discussion. In particular, oftentimes you'll hear something like this: the flux, it counts the number of field lines that go through something, right? And so you might wonder, what does this mean? Field lines, right? So let me try to give you an indication of what that looks like. So for my first example, suppose we've got the vector field F is equal to x hat. I'll tell you what, I'll make it more interesting. Plus y hat, there you go. So what's this vector field look like? It's a constant vector field. Everywhere it just points along the line y equals x, or its parallel translates, right? So, basically, if I draw these lines, these are, you might call these field lines. They're the integral curves of the vector field. They line up with the vector field. If I take a particular point in space, and I look at that point, like, say, this one, then, well, maybe a point on this right here, then, of course, the vector field points like that, right? But you don't want to draw, in this way of thinking, you draw field lines instead of the vector field itself because it's kind of a pain to draw infinitely many arrows, but it's a lot easier to draw some curves, right? Now, in this system, in this concept, you could also look at something like 2 times f. All right? Something like 2 times the vector field. And the convention is, well, what would the magnitude of 2 times the vector field be versus the magnitude of f? Like, magnitude of f is what? Yeah, magnitude of f is square root of 2. This new vector field has magnitude 2 times the square root of 2. It's twice as strong, right? And if you're a fan of this way of thinking of vector fields in terms of field lines, what you do is you draw more field lines to illustrate stronger magnitude. So if I wanted to illustrate 2f and f in the same thing, so like basically just double up the number of lines here. So the blue and the green taken together would be the field lines of 2f. Okay? So how do you define what is flux then? Flux is a measure of the number of field lines that cross the object, or let's say cut through the object. Now, so I'm being a little bit vague because I want to talk about flux later for vector fields in 3 dimensions, and later I want that object to be a surface. All right? But for today, talking about 2-dimensional things mostly. And so the object I have in mind for this discussion is simply a line segment. All right? So like the line segment might be like this line segment. Well, I'll just make it all the way across. How about that? Suppose thinking about this line segment L. So what would the flux through L be? We use the symbol phi for flux. So the way this works is it's something like, well, how many field lines cut through L? 1, 2, 3, 4, 5, 6, 7. Oh, did I do 7? I did do 7. I guess I needed to add another to double the number of field lines. Where should I put it? Sorry, it's bothering me. I wanted to have 2f have eight field lines for the, so this one had 4. I should put another one over here to be fair to 2f. There we go. Why didn't you guys call me on that? Can't you count? That's right. I'm talking smack about you. That's what I do. All right, so this is 8. Because there's 8 lines that cut through that line segment L, so the flux is 8. Right? Yeah.
Does flux have units?
That's a good question. So what, I mean, this is with respect to this whatever system of units I've made up here, which is kind of vague. It's just based on the picture. I'm really just going to be able to make comparative statements in my toy example here. On the flip side, if I was to take, say, this line segment, right, and maybe the same length but at a different angle, like this one, right, like the same length line segment, but let's call this L2, the flux through L2 would be what? Well, you can see how many cut through it. 1, 2, 3, 4, 5, 6, about 6. What if we took a line segment L3 that looked like this? Yes, the answer is 0. No field lines cut through this. So when we talk about the field lines cutting through the object, we must insist that the field lines are going through like the they're parallel to the perpendicular of the object. If they lie tangent to the object, that's not cutting through it. That's just skirting along it. All right. Now, as Luke was starting to pick at, like, what are the units here? What do you really mean? What I'm trying to give you right now is just a qualitative picture of what we mean by flux, right? I will be quite quantitative here in a second, but a good rule of thumb is that the flux, to fix the units for flux, what we're actually going to do, is something like this. If my field lines are whatever direction, I don't know, and I look at like a little line segment L, then to a good approximation, if the field is like this, then the flux through this little line segment L, what it's going to be defined to be is just L, and let's think of L as a vector, right? Well, maybe not. Let's think of L as the length, L and F, and then we dot with what? The normal. And so for a line segment, that's ambiguous, which direction's the normal. But it will be unambiguous in what I'm about to define. So let's just say that that's the side we want to count as positive if it goes that way, if the vector field goes in that direction. So this would be the flux through a little line segment of length L. Basically, it's proportional. The flux should be proportional to the magnitude and to the length of the object for two-dimensional flux. That sets a scale on it. So qualitatively, if you're drawing a picture of vector fields in 2 dimensions in terms of field lines, you can get a sense of how, the strength of the vector field in terms of the density of the field lines. And for a given line segment of a particular length, if you move it around, the more lines it cuts through, the greater the flux through that little line segment. Okay, but we're not content with this notion. We want to define the flux through a closed curve. A simple closed curve, also known as a Jordan curve. It's a curve that has the property that it works for my joke. In other words, it defines an inside and an outside to the plane. If you remember my stupid joke. So a simple closed curve like a circle or a loop. Figure 8 is not allowed. It doesn't have any self-intersections except in the sense that it comes back to where it started, right? That's the only intersection that you can think about. Simple closed curve, the flux phi through a simple closed curve of a vector field f equal to p comma q is the integral, let's see here, flux is equal to the integral, make sure I don't make a stupid sign error here, of, well, it is impossible to make a sign error at the moment, f dot n ds. So you take the vector field, you dot it with the normal, ds, like this, over the curve. So it's defined in terms of the integral with respect to arc length. Now this unit normal, which kind of unit normal do I mean? Where n hat is the outward pointing unit normal. I think it's let's discover the better formula for this. We don't take particular joy in calculating integrals with respect to arc length. We'd much rather do an integral with respect to dx and dy, right? That's kind of our happy place. So here's a picture of a particular curve. Could be something like this. I don't know. Whatever. Oh, that's too complicated. Forget that. There we go. Good enough. So and I'm going to suppose that it's counterclockwise oriented, which means that its direction is like this, right? Counterclockwise. So the unit tangent looks like this, right? So here I plotted the unit tangent in black. If I was to plot the Frenet normal, where would that be? Where does the Frenet normal we talked about earlier in this course point? Towards the center of curvature, right? Towards the center of the osculating circle that you could fit to the curve at any point. So the Frenet normal, at most points here, sometimes it's inward pointing, right? Like here the Frenet normal's like this, right? But goodness, over here the Frenet normal's out here. I mean, the Frenet normal, to understand where it's going, you have to picture this curve in 3 dimensions. It kind of, sometimes it flips outside. I mean, it kind of flips over and outside and inside. And that's not good for calculating flux, right? So the Frenet normal is definitely not what we need. We need something else. I mean, it's graphically easy to picture. It's this, right? This is what we need. This is n hat. Right? Now, so what is that in terms of dx, ds, and dy, ds? I mean, t, you can write as dx, ds, dy, ds, let's say, okay? With respect to the arc length parameterization of the curve. So how is n related to that? When x is increasing, right? When x is increasing, it looks like, see here, when x is increasing, it looks like it's pointing down, doesn't it? When x is increasing, it's pointing down, isn't it? Look at that. Every place where x is increasing, it's pointing down. Every place where x is decreasing, it's pointing up. So it must be that this is minus dx ds for the y component. We got 2 choices, right? Because n has to be perpendicular to t, you're either going to do minus dy ds dx ds, or you're going to do dy ds minus dx ds. And I claim from the geometry it's clear we choose the latter. So this has got to be dy ds here. And you can look at that and verify that that's reasonable. If y is increasing, this should be pointing to the right. Where is y increasing? Let's see here. Y is increasing basically here. Y is increasing. So basically y is increasing along this stretch of it right here. Y is increasing, right? And in that same place, n hat should be pointing to the right general direction. As you can see, that's the case. And let's see here, y is again increasing right up in here, right? Again, the outward normal should be pointing to the right. If you study this formula carefully, you can see it's quite reasonable. And so with that in mind, you see we found a better way to calculate the flux of a curve with respect to a vector field. If we just put this up in here, we get what? Integral over the curve of f dot, well, let's write it out this way. P comma q dot dy ds minus dx ds, and what does that give us? I mean, formally, the ds's cancel. Less formally, if you work through the definition of the line integral with respect to arc length, well, the line integral with respect to arc length is precisely equal to this specific line integral, which we've defined carefully in previous classes. So there you have it. That's the flux through a vector field. Flux of a vector field through a circle. So let's see here. Let's do an example before I get too carried away here. Let's look at the vector field f of xy equal to xy, and let's let c equal the unit circle. I expect that the flux of this should be non-zero, right? Because if you picture it, f looks like, in fact, from the geometry, I think I can already tell you what the answer is going to be. I think the answer is going to be 2 pi, because the length of the circle is 2 pi. Oh, and the magnitude, oh, no, it should be square root of 2 times 2 pi, I think, because the magnitude of this vector field is oh, no, 2 pi. The magnitude of that vector field is, in fact, 1 as we look at the unit circle. Let's work it out, though. So the flux is the integral over the unit circle of p dy minus q dx, but this is equal to the integral from 0 to 2 pi. Now my p is what? Oh, excuse me, one more step before I write details here. P is what? P is x dy minus y dx. What's the unit circle? X cosine theta, right? Y equals to sine theta. So I've got myself dx is minus sine theta d theta, dy cosine theta d theta. So we plug those in. Gives me what? Cosine squared theta plus sine squared theta, because the minus and the minus go away, d theta, 2 pi. Which is really unsurprising, because if you took this circle and just unwrapped it and laid it in a line segment, you just have a vector field of magnitude 1 crossing the line segment of length 2 pi, exactly perpendicular to the line segment everywhere it crosses it. All right. So that is flux through a curve. Now, I want to go through a little argument with you to try to discover something called Green's theorem. A lot of books, what they do is they just write down Green's theorem as if it's from just, I don't know where, just like, well, people knew it before you, so you should accept it, and then they show you a proof that's mathematically true for a graph. And I think that's great, but it kind of leaves you with a feeling like, where did Green's theorem come from? I want to show you a little argument to try to motivate where it's coming from. And so what we're going to do here is we're going to look at this little rectangle. I've pictured a vector field f. It's got two components, It's got the, the x component's p, the y component's q. And what I want to do is I want to calculate what's the flux through like a little rectangle, which I've drawn the rectangle like it's rather large, but conceptually I want us to think of this rectangle as being like infinitesimal. All right, think of it as being a very small rectangle in principle. And the question that I have is what's the flux of the vector field f through this little rectangle? So all I have to do is find the flux through each side and add them together. Okay? So let's get started. What would the flux of this vector field be through the base? You take n hat, right? I mean, in each case, we're going to take f dot the normal times the length of the line segment, right? The length of the rectangles here, it's either change in x or change in y as I've set it up. All right? So let me number these. 1, 2, 3, 4. Okay, so number 1. What do we got? N hat is what? It's actually minus y hat, right? Minus y hat dot this vector only cares about q, right? So I could say that that's just q of, say, xy times, what's the length of this? Delta x. That's the flux for 1. What's the flux through side 2? Oh, and that's not quite accurate either, is it? What am I missing? It's kind of important. The minus, right. How about the second one? N hat is actually equal to x hat in this case. That's the unit normal. So if I take the dot product of the vector field with that, I would get, it ignores the blue part of the vector field. It's completely about the green part. I just get p of x plus dx, comma y, delta y. We're thinking of this as being an infinitesimal rectangle, so I'm trying to pick either one of the endpoints to set up the magnitude. You could take the midpoint if you'd rather be more fair, but in the limit it won't matter. We'll see that. That's a good approximation, at least, of the flux, right? What's the approximation is the assumption that the vector field is approximately constant as you go across one of the sides of the rectangle. In other words, it doesn't make a difference whether I use p of x plus delta x comma y, or if I use p of x plus delta x comma y plus delta y. It won't much matter. To be fair, maybe I should use the midpoint. Whatever. Phi 3 then, what? This time n hat is y hat. So, yeah, positive q of, let's say, I guess I don't know, whichever, I'll use one with less writing, x comma y plus delta y. And the length of this is delta x. So that's the flux through that side. And finally, the fourth one. So here n hat is minus x hat, right? The q is ignored. The p gets a minus, so I get minus p x comma y delta y. So the total flux is a sum of these 4 pieces, right? So net flux around the rectangle, which, well, I would say the boundary of the rectangle, really. So the flux around the boundary of the rectangle is, I'm going to write it somewhat suspiciously as p times x plus delta x, comma y, minus p of xy. I'll factor out the, what do I got there? Delta y. plus q of x comma y plus delta y minus q of a bit of xy factor out the delta x. Yep.
If you take the limit as change in x and change the y to 0, doesn't that mean the flux through a point is 0?
Well, the flux through a point is very tiny, but we want to capture that in the same sense of like 0 over 0 in calculus 1, right? So to get at that, what I need to do is divide by something else which is tiny in such a way that we don't lose track of, we don't want to go too far and get infinity, right? We're going to go just far enough to discover something interesting. To do that, we divide by delta x, delta y. Yeah?
Yeah, but it's almost like a different expression.
Right. In fact, it will become that. I'm glad you guys see that. If we divide by delta x, delta y, right? Which would be a natural thing to divide by, right? Because what's the area of this rectangle? It's delta x, delta y, right? So if we take the flux and divide by the area, which seems like a natural thing to divide by anyway, to gain some measure of what it is, we've got p of x plus delta x, comma y, minus p of x, y over delta x. Well, that's cool. Plus q of x, comma y plus delta y, minus q of x, y over delta y. Then, as delta x, delta y both go to 0, we obtain what I would call the change in flux per unit area is equal to partial p, partial x, minus partial q, or rather plus partial q, partial y. Which we can recognize as being the divergence of the vector field PQ. See, so the divergence measures how the flux diverges around a single point, around close to a point for a given vector field. And now I've only shown you this for an infinitesimal rectangle, but if you were willing to make a little jump here, which I will motivate more completely a little bit later in this lecture, jumping ahead a bit, we discover Green's theorem, which states the following: the integral, the double integral over R of partial p, partial x, plus partial q, partial y, dA is equal to the circulation, well, the flux of the vector field, which is where we're calculating. So the flux of the vector field will be integral of p dx minus q dx, p dy minus q dx over the boundary of the rectangle. And this is, in fact, the divergence form of Green's theorem. Let's see here. What if I tried to apply this to the unit circle? How would that have gone? Let's go back and do my original example about flux using Green's theorem instead. How would that work out? Let's revisit it with Green's theorem. So we'd say the integral of x dy minus y dx over the boundary of the unit disk. So let's say that the circle is equal to the boundary of the disk, right? The unit circle is the boundary of the unit disk. We agree? I hope we agree. Well, you can disagree if you want, but you'd be wrong. Okay, so that's your prerogative. If I apply Green's theorem, if we believe it, hopefully you'll believe it by the end of today, we will prove it, I can trade that flux integral for a double integral right? Double integral over the disk itself, right? Of what? Partial p partial x plus partial q partial y. Partial x of x plus partial y of y. Which is what? See, this says that p is equal to x and q is equal to y, because when we look at the flux, we have to look at the coefficient of dy as being the p, and minus the coefficient of dx as being the y, as being the q in the vector field we're finding the flux for. And so what we have is twice the integral of dA. What's the area of a disk, of a unit disk? It's pi, so 2 pi. Is that easier than the calculation we did before today? In fact, it is. Right? Now happens to be because we know the area of a unit circle is pi, but oftentimes Green's theorem it's a lot of times the case that double integral might be easier to calculate than the corresponding line integral, and that's the power of Green's theorem, is it trades one kind of integral for another, and that kind of flexibility can be a great asset to us in certain calculations. Okay, so there is yet another way of looking at Green's theorem. What's the other thing we talked about? I haven't talked about flux before today. What else we talked about before today for vector fields? What was our primary interpretation of the line integral? Was what? How did we define the line integral? What was it to calculate? I mean, physically speaking, we could say it calculates work, or we also said it measures the circulation of the vector field around the curve, right? So the other way we could look at this is to draw the square again, like draw the little rectangle, right? And again, kind of replicating what I just did. X, y, x plus delta x, comma y, x plus delta x, y plus delta y, and x comma y plus delta y. Again, look at the vector field. This time I'll look at, still looking at the vector field f equal to pq, all right, same vector field. But this time I want to calculate what's the circulation around this infinitesimal rectangle, right? What's the circulation? What's the circulation? Or work, if you like. So let's again, 1, 2, 3, 4. So we calculate what's the circulation on each piece? It's what? It's basically f dot dr. Or if you like here, we could think of it as f dot delta r. Right? We need to calculate this for each line segment. What's the unit tangent? And we're assuming counterclockwise orientation, all right? So here we have t, or this would be f dot t times the length. Just like before we calculated f dot n times the length. This time f dot the unit tangent times the length. Here t is equal to x hat. Here, what's the unit tangent? Y hat. Here, t is equal to minus x hat. In case 4, the unit tangent is equal to minus y hat. So what I get then is the work, or circulation if you like, maybe work's a better term. The work in part 1 is equal to f, So this one, when you take the dot product of the tangent times the vector field, what do you pick up? You just pick up the p, right? So this gives me P of x comma y delta x. For work 2, I get what? Q of x plus delta x comma y times delta y. How about the work on the third part? Looks like minus P. I'll do x comma y plus delta y times delta x. And the work for part 4 is what? Minus Q x comma y plus delta y. Or xy is easier to use. I'll use xy. X comma y delta y, right? So how do we calculate the net work? Go for it.
P and Q in a force field, or the vector field, they're functions of x and y.
That is true, yes. No, yeah, we're thinking about the vector field being a function of position, right? Other questions? So the net work is 1 plus 2 plus 3 plus 4, right? And if we take that and we divide by delta x, delta y, what do we get? Get straight to the point. We get Q of x plus delta x comma y minus Q of xy, and the delta y's cancel, you're left with delta x minus P of x comma y plus delta y minus, big parentheses here, P of xy divided by delta y, because the delta x's next to the p terms cancel when we divide by the area. Yes. Yes. Indeed, a minus is a plus. So what this shows us is that the work, in some sense, per unit area, right? As delta x, delta y go to 0, we obtain something like the work per unit area is partial q, partial x minus partial p, partial y. So if you integrate this and jump ahead a bit, this leads us to the other version of Green's theorem, namely the double integral over the rectangle of partial q, partial x minus partial p, partial y. All right? Integral of that over the area should be the same as just the work around the boundary of the rectangle, counterclockwise oriented, of p dx plus q dy. And I would say that this is the more standard version of Green's theorem. You see this more places. There's less of a tendency we have to make a sign error using this. You see there's something kind of unnatural about having to look for q as minus the coefficient of the dx in this formulation of Green's theorem. This invites a sign error. This is less prone to students making sign errors, so we teach this, most people. In fact, most people, when they start talking about Green's theorem, will just state this and go on. If you don't have enough time, you start with this and show how it works. We have a little bit of time, so I try to explain things to you. But this is also known as the what? If that's the divergence form for Green's theorem, this is in fact the curl form, or the work form. I would say this is the curl form of Green's theorem. Now the reason I say that is if you calculate the curl of p, q, 0, you know what you get? you get 0, 0, and qx minus py. In other words, in fact, this is the z component. That's the z component of the curl, and that's no accident, because z hat is also the unit normal to the rectangle if you envision the rectangle in 3 dimensions. This identification is important to us later when we try to prove Stokes' theorem, so I hope you heard what I said and understood it. Or not. You can talk to me after class, whatever. It's cool. All right. Neither of these are proofs, right? How do you actually prove this theorem? I don't know about you, but I'm tired of writing, so. But I should keep writing. I shouldn't be lazy. All right. Oh, yes, question.
Aren't these two about the same if you substitute negative q for p in one of them?
Yes, indeed. If we prove one, we get the other by substitution. That's also true. But the interpretation is so radically different, right? I felt like, yeah, logically speaking, I could just go, well, if you plug in blah over there, then you get this. But I think it's important to understand. This ultimately gives you a better answer for why we talk about curl and divergence at some point. So, okay, so if you think about regions in the plane, right? So let's think about some kind of region in the plane that's bounded by a simple curve, a simple closed curve. That would be what's called a simply connected region. Such a region, you can shrink loops to a point without getting stuck on anything. So, if this is a typical simply connected region, whatever. And so if you, this is neither type 1 nor type 2, right? Like, yeah, this is not type 1. That's okay, but, But if you look at it, you can maybe parse it into, let's see here if I can, I can't illustrate it worth anything. I need something simpler. I'll do like a lima bean. So I think if you study this long enough, you could probably see how to cut it into pieces. Well, maybe that. I don't know. Maybe this. I think if I keep cutting long enough, you'll see I can cut it into a bunch of regions which are both, like they have a common. If you look at each one of these regions, they're both type 1 and type 2. So in other words, there is, I can divide it into left and right and top and bottom. It's just a claim I'm going to make at the moment. I'm not sure that I have illustrated it yet for this one. It's just that time of the day. But let's just focus here. If it's both type 1 and type 2, it would look something like, something like this, more or less. Roughly speaking. So there's, one thing's the top and one thing's the bottom, and also one thing's the right and one thing's, left and right are well defined. So in other words, this region, we have the following set of inequalities to describe the region. We could say A less than or equal to X less than or equal to B, and, how to say this, F1 of X less than or equal to Y less than or equal to F2 of X, right? That's the type 1 description of it, right? But if it's simultaneously type 1 and type 2, I can also, in the same breath, I can describe it in terms of the inverse functions of F1 and F2, right? I can say, this This can also be solved, like I can solve, this would be y equals f1 of x, right? In my picture. So I can solve that for x is equal to f1 inverse of y, and I can call this thing g1 of y, or I can call it g2 of y, as I will actually. And so, likewise, if these points are, let's say, a comma c, b comma d, I also have c less than or equal to y less than or equal to d, and g1 of y less than or equal to x less than or equal to g2 of y. I can describe the region, this lemon-shaped region, in terms of both type 1 and type 2 setups, right? Excuse me. Oh, energy depleting. Okay, so I'm going to pick on this version of Green's theorem to try to prove it for this region, which is simultaneously type 1 and type 2. All right? And the proof is going to break into two pieces. Actually, to prove this, you can trade this for proving two things, one of which I may have left as a homework, although that's kind of not too mean, because if you search the archives, you'll see that I have it proved in the archives somewhere. So we could prove this and prove this. If we can prove these two things separately, then we have it. And the mathematics is nice here. It allows you to divide and conquer. So I leave the Q piece to your homework. I'm going to prove the P piece. Okay? So I'm going to try to show this for the rectangle, not for a rectangle, but for a region, which I have attempted to picture over here, that's both type 1 and type 2. And my claim, which I can't convince myself of today in terms of my stupid picture of it, I think it's a reasonable claim, though. You could take any arbitrary simple closed region and divide it up into a bunch of these that cover the whole thing, simultaneously type 1 and type 2. Okay, anyway, so before I get distracted again. So which side do you think I should start on here? Should I start with the, which side should you try to, I mean, I got to either go right to left or left to right. I think we're going to go left to right. Let's start with the double integral, see if we can't convert it to the line integral. So double integral over R of, and I'm going to put the minus, I'm going to leave the minus, I'm going to start with minus this side, okay? So I'm going to start with just partial p partial y dA. Now I got choices, right? I can either set it up as a type 1 or I can set it up as a type 2 integration. What should I do? I want the y to go away, so I'm thinking I want to do, oh, I don't trust my thinking. Let me look at my notes. Where'd you go? Yeah, set it up as type 1 in this case. So I do integration from a to b, integration from f1 of x to f2 of x, and then I do partial p, partial y, right, of x comma y, dy, dx. But this is pretty awesome because in the first integration, we're faced with the integral of a total derivative with respect to the integration variable, which means by the net change theorem, I can just do the first integral by fundamental theorem of calculus. This is p of what? P of x comma f2 of x minus p of x comma f1 of x. Where was I? Dx, yeah. But then what? You can break it into two integrals, right? I'm going to write this somewhat suggestively as dx over dx. Dx. dx over dx. A little bit. Maybe if I rewrote that in terms of if I trade all my x's for t's. Well, anyway, let me stop behave. So if you look at the picture here, let's see here. I need to say which ones. Say f. This is y equals to what? Y equals to f1 of x. Top one, I said y was equal to f2 of x. We need some labels here. Let's say that we're going I want to go counterclockwise, right? So this way and then that way. So this is C1. This would be C2. So, okay. So C1 has x equals to x, and y is equal to f1 of x, right? That's a parameterization of the first curve. So if you look at this, this is straight up just the integral over C1 of p dx. So we have minus the integral over C1 of p dx. The other piece, C2, right? Well, minus C2 is better because then we can say x is equal to x and y is equal to f2 of x. The reason I use minus C2 is so that I can use x as a parameter, right? I can't, C2 has, it's going in the negative direction, so minus C2 has x going in the right direction, so I can use x as a parameter. So with respect to that notation, of course, this is precisely the integral over minus C2 of p dx. So what do you have? You have the integral minus the integral over C1 union C2 of p dx. In other words, the integral minus the integral over the boundary of the region p dx. And there's half of it. The other half follows through a very, very similar argument, where instead of doing the y integral first in the iteration, you do the x integral first in the iteration. When you do the x integral first, fundamental theorem of calculus integrates the partial q partial x to like q evaluated on the left and right curves, which then give you integral over C1 and integral C2, much similar to this. So there's a proof that works for a simultaneously type 1 and type 2 region. Now, if you're like me, I can't always see how to parse a given region into type 1 and type 2 regions. It's just some sort of like geometric vice I have. I don't know. So I would like to show you another way to look at this. And then I would like to show you some examples. Let's see here. By the way, the next homework is not due tomorrow. It is due Monday. So I don't know why you guys are always so happy about not doing my homework on a given night. I personally find doing my homework the most rewarding part of my semester. Well, that's not entirely true, but I used to love homework when I was an undergraduate. My favorite part of the whole experience. Yeah, I think as a university we should make more of an effort to make more of your time about studying and less of it about activities. This is, after all, a university. But then again, I'm kind of crazy. I got lots of weird ideas, like students should be studying, I don't know, whatever. But ninja problems, yeah. Those are not as... All right, come on, where'd you go? Yeah.
Question. When you say that a region is both type 1 and type 2, is that the same as saying that the curves that Kramer tried on the outside bounce pass both the vertical and horizontal lines?
I think that's what it amounts to. I mean, because I can, they're injective anyway. I have to be able to solve, yeah. Now, I'm glad, though, that I have another proof. Let me show you. And this is important, actually. This argument I'm about to show you, it's the first time I'm showing you this argument, but it won't be the last time. All right. So, another way to look at this is the following. We've done this calculation, right, for the little rectangle. That little rectangle is arbitrary, right? So I can take the closed region, I can take the simple curve, simple closed region, and I can chop it up into a bunch of little rectangles. Now that I can do in any given day, I can do that. That's not as hard as the thing I was trying to do over there with type 1 and type 2. Geometrically, it's clear. You can take any shape and chop it up into a bunch of little rectangles. Now, you might need infinitely many, right? So you're probably going to need infinitely many, honestly speaking. I mean, they're going to get lots and lots and lots and lots and lots and lots and lots of little rectangles to fill in these kind of things, you know? But that's okay, because you also know that their values are going to converge in some sort of meaningful way if you wanted to do the analysis, whatever. Now, here's the cool thing. To calculate the net work, all right, done around this whole shape by a vector field, it turns out that the work that are done by interior edges to rectangles, they're always experienced both in the positive and the negative sense, because these rectangles are adjoining one another. And every interior, what I call crosscut, so this, for example, this one and this one, both counterclockwise oriented, right? So this upper edge of R17 goes from right to left. The lower edge of R16, which adjoins R17, goes from left to right. So they're, what'd I do? Like this. But it's the same geometric thing, they're just, it's the reversal. So all of the edges are reversals of one another wherever they meet. The only thing that's left, if you add the work over all the rectangles, the only thing that's left, the net contribution of the work around the edges of all these rectangles, is just the exterior boundary of the whole thing. So if I add together the work done along each counterclockwise oriented subrectangle here, and I add them all up, that should in total give me the work done by the vector field along the exterior of the region. On the flip side, you can add up the flux from each little area, right, times the area of the rectangle. And if you think about that for just a second, you'll see that as you pass to the number of rectangles becoming infinite, that's exactly the area integral of this, this particular partial derivative function. In other words, I can just integrate the thing we found from the little rectangle up by just adding it up. And the cool thing about the canceling of interior work integrals gives you that the sum of the works is the total work around the edge, and hence Green's theorem. And the same thing can be said for the divergence form. All right? Now, I'm not going to talk to you guys about Green's. I will talk about Green's theorem for an annulus tomorrow. I'm not going to talk about Green's theorem for an annulus today. I decided that should have its own day. Let's not try to talk about that today. What I want to talk to you about now, for the remainder of class, is something